This conference will now be recorded.
Okay, so welcome everybody. Uh, Today we have a presentation by Dan Biederman. So a little bit about Dan Biederman. Dan designs and architects networking and storage ASIC and FPGAs for the last 25 years. He has worked on both large-scale companies as well as startups. He has been working with precision time synchronization technology since 2006. At Cisco, he helped develop their first industrial precise time switch, the IE3000. At Ericsson, he continued to help with synchronization in cellular networks. And for the last 5 years, he worked in Intel on infrastructure processing units, continuing to promote precise time technology. He has a BS in electrical engineering and a master in electrical engineering from Tennessee Technological University. Well, never heard technological. He has been granted over 30 patents worldwide. Awesome. Then and today's presentation from Dan is about precise time applications. So I'm glad to have a little bit we're trying to get some balance between why and how. So today's presentation is more about why. I mean, usually I am more leaning toward the how. So it's good that we have a little bit of why and why we do these things and motivations and so on. Anyways, with no further ado, Dan, the floor is yours.
All right, thank you very much. So as he mentioned, my name is Dan Biederman. I'm a technical leader in the Ethernet products group here at Intel. And so let's begin. So the agenda today is I'm going to do things a little bit different. I'm going to start with a love story and then talk about precise time today, the processor's use of precise time, the trends in precise time and ideas for the future, and then we'll have the conclusion and Q&A. So, as I said, we're starting off a little different. Let's talk about a love story. So once there was a high school senior who fell in love with a girl. She got grounded because she had bad grades. And so the graduating senior decided that he was going to save up all his money so that he could spend it on the girl once she got ungrounded. And sure enough, he saved in a few months $2,000. However, he found out that she liked someone else and it was over. So he had $2,000. What did he do? He spent it on his next love, an Intel 386 SX computer with the turbo button and a printer. And so in the college years, our hero wrote, papers on the computer. He ran simulations on the computer. He played games and he met people through the computer and helped people. After graduating, he went on to his master's degree looking at logic design, computer architecture, and artificial intelligence. But unfortunately, doing his master's degree, that Intel 386 SX was just too slow to run the latest training programs for artificial intelligence. He would never finish. So luckily, the university got a few Intel Pentium workstations. They ran at a massive 90 megahertz, and he was able to use these machines to train his neural networks and complete his thesis and graduate with a master's in EE. And in that time, he met the love of his life, and they were doing their masters together, and they both wrote their master's theses on that 386 SX computer. So you can see that our hero here has, an affinity towards computing and a love for the computing. In industry, basically worked at Cisco on their first industrial Ethernet 1588 product and supported other groups with their 1588 efforts. He worked at 2 startups, was later hired by Ericsson for his time sync experience, and now being part of the Ethernet products group at Intel, he's doing wonderful things with precise time synchronization. But he needs your help. So what precise time tools are available today? Well, we've had many presentations here at OCP TAP about 1588. It's available on most NICs and FPGAs, even available to the processor for example, the NEOS 2 processor in the FPGA. And we've had some presentations here at OCP TAP about White Rabbit for very high precision and accuracy. On top of that, now we're getting precise time to the processor with PTM, and this allows, PCI or precise time across the PCI network. On top of that, now that you have precise time at the processor, applications can take advantage of it and instructions can take advantage of it. For example, one instruction is this read TSC, which we'll learn a little bit more about in a minute, and then the instruction tpause. So also, Kevin Stanton presented several months ago about how you could use get CPU time using this clock get time to figure out the monatomic raw, the monatomic in real time, or a triplet of the Ethernet PTP time, real time, and the monatomic raw time. So let's talk about read TSC and pause. So read TSC allows, or RDTSC allows you to read the timestamp counter. You can actually look it up in the instruction manual, and you'll get a page that looks like this. It has a lot more descriptions that you can look at. And then tpause is an instruction that waits for a value on that TSC, the timestamp counter. And this is what it looks like if you look in the software developer's manual, which I've given a link at the bottom. So now let's take a step back. Let's look at a real-time use case. And I get this use case from a PE here at Intel named James Coleman. And thinking about real time, our lives are real time. So a lot of things like getting to the airport or getting to the ferry, or dropping your kids off at school, you have to consider real time. So he likes this ferry example, and I like it as well. So you need to get to the ferry by 10 o'clock in the morning. If you're late, the trip is useless. You have to wait for the next ferry or do something else. So what do? Well, first thing you need to do is look at the timetable. When will the ferry be leaving? And the captain must meet that schedule, and me trying to get there, I'm dependent on that schedule being met. If it's a 20-minute trip from your house, what do? You leave about 30 minutes early, giving yourself a 10-minute buffer. And as you're driving, you check your watch. If there's heavy traffic or construction, you try to drive faster where you can. Maybe use the HOV lane, even if you're just one person. You try to run, get through those stoplights as quickly as you can, and maybe you glide through the stop signs doing a California, stop. And if you ever hit a point where you can't get there by 10 a.m., you missed it, you turn around. So in real-time computing, you have similar things, right? So in the Internet of Things, there are real-time computing situations. You must complete a task by a defined time. If you don't complete that task by a defined time, you risk, not meeting, your obligations, or in some cases in IoT, there could be functional or safety issues if you don't meet that time. And so what do? You basically give it for the worst possible time, that 6 nines, and you throw extra processing at the problem. But what could you do? Could you look at the ferry example, monitor the process, and the time, and what do you do if you're running late? So looking at the ferry example in real-time computing, you have the schedule. Well, for the ferry, you have the ferry timetable, which is probably in minutes. In real-time computing, you have the application or your schedule or your service level agreement that you have to meet. For your time base, your wall clock, watch, cell phone, you're looking at things in terms of minutes again. And here at the real-time applications, you have GPS time or 1588, PTM, White Rabbit time, and you're looking at things at nanoseconds, or in the case of White Rabbit, in the picoseconds. So if you want to get improvement, we talked about, hey, I'm going to drive faster to the ferry. Well, you can speed up the processor clock. You could try and run a little faster. Maybe you use a little more power than you wanted to. That turbo boost on that 386 SX computer. talked about you could use the HOV lane when you're not supposed to. You potentially, if it's a multi-processing computer, you could slow down tasks that other processors doing, knowing that this task needs all the resources that it can get. I talked about, you could try and run those late yellow lights. You can punt tasks to other processors. So if you have 5 tasks to finish, you could potentially punt other tasks to other processors to try and get them done in parallel to help you meet your schedule. Talked about California stops, gliding through those stop signs. You can allocate more resources to the tasks. And if you're late, what happens in the ferry? You miss the ferry, but here you miss your SLA. Your performance of your applications go down. You don't want to be late. And when we talked about checking time, you're checking your watch, your car clock. Here you could use read TSC if you're doing your timing based off the timestamp counter, or you can use those other clock mechanisms that Kevin Stanton brought up a few months ago. So I really like the idea of using precise time and instructions, and this TPAUSE is very interesting. So I created a no-op wait instruction, which basically I wrote a white paper on, and you can actually get it at the link below. And basically the Intel allows you to add instructions to the NEOS processor. So I basically created a no-op instruction with the help of my partner there, Dennis, and we basically allowed this instruction to wait in a loop, basically looping on itself for a precise time. And then once that precise time was met, you would move to the next instruction. It's similar to the TPAUSE instruction, this no-op wait instruction, but there are no power saving modes that you could take advantage of. And this white paper then continues to go on and show, real world examples of how you might be able to use an instruction in the NEOS processor that uses precise time. And Dennis actually built this, the NEOS instruction, and downloaded it into a Max FPGA board and actually got it to run. One of the applications that we talk about in this presentation is this time-based semaphore. And semaphore is basically a mechanism that allows you to, control the access to a common resource. It's basically a locking mechanism. With the no-op wait instruction, precise time can be part of that locking control mechanism seen by the processor, in this case, the NEOS 2. And it can be used to reduce traffic and reduce congestion. This is, instead of the ferry example, let's look at the freeway metering light, right? You could think of a semaphore as I'm going to give a car an access to the freeway every 7 to 15 seconds. But in this term, we could use 1588 time and do it in nanoseconds or microseconds, whatever granularity you want. But the goal, for the freeway metering light is to keep the cars, moving on the freeway, reduce congestion, and in turn reduce accidents. With a semaphore, you're reducing congestion, trying to get access to that locking mechanism, and trying to avoid the case where 2 people get access to it at the same time. And so one other way that you can use this TPAUSE or no-op wait instruction is for a TDM-like scarce resource usage. So you can use the instruction to delay the start of another operation. You can use it to stagger windows. You can use it for, this kind of pacing of instruction or in pacing of applications. And in this example I show here is that some operations take longer than others, but they all fit within the window. And it's very useful if you're doing the same sort of operations over and over again, like you're doing packet processing over and over again, or doing some sort of encryption or AI ML type operation. And so on the picture on the right, you can see that we have 4 processors. One of them paces theirs at the beginning. and we'll go through that a little bit more in the next slide. So let's say you had a goal of doing 100 million operations per second using 4 processors. Examples of those operations could be packet processing, they could be database operations, they could be Internet of Things operations, or AI, ML, artificial intelligence type operations. So in this case, since you have 4 processors, they need to basically do 25 million operations per second per processor, and that basically means 1 operation in 40 nanoseconds. And so if you look at the picture on the right, we have those 4 processors, the blue, the green, the yellow, and the purple. And for the processor 0, it would start at, say, 0 nanoseconds. Processor 1 would start at 10 nanoseconds, processor 2 would start at 20 nanoseconds, processor 3 would start at 30 nanoseconds, and then we'd go back to processor 1, 2, 3, and we'd basically pace when they would start using this TPAUSE or no op wait instruction. So why would we want to do this? Well, if you think of the worst case where you had 4 processors processing the same type of information, there's a chance that they could all align. And since they're unstaggered, it can lead to inefficiencies. So breaking, the 4 processors now into 4 different resources that you're using, which are A, B, C, and D, or blue, green, yellow, and purple, you can see that all the A's line up at the same time. And because of this, since the events are not synchronized, they can be bursty, cause contention, and add latency. And if you look at just the A process, you can see this burstiness in that all of them are trying to access that or perform that A operation at the same time. And that resource that's providing that A operation, now needs to handle 4 times the processing required. And thus it's like 4x processing, do nothing for, 3 times, and then 4x processing. So it's very bursty. It can lead to congestion to a resource and hence latency. And this example shows 4, but if you actually consider, some of the multiprocessor systems we have, they could have 64, 128, or more processors trying to access similar or the same resource. And thus, it makes things more bursty, more congested, and adds latency. Examples of these might be, A might be your ingress data, D might be your egress data. You might be looking at accelerators for B and C. And so, but if we stagger this, then there's less congestion, and there's less burstiness, and you kind of even out the processing at the scarce resources. And the latency should be ideal as only one processor or processing element is accessing the resource at any given time. And hence, there's a lot of value in using precise time to stagger these accesses to these resources. So let's look at another way that we could use TPAUSE to use precise scheduling, resulting in what I consider precise software timestamps. And that's basically, you're going to precisely time an event or access to a resource. This could be the creation of a packet or the start of a routine. And this is a pure software solution. You don't need to have new hardware added to a processor or anything like that. But being purely software, there are things that can add jitter, like out of order instruction execution and the reading of the time itself. And so let's look at this. So let's say you want to do something like you want to timestamp a packet's departure, and you could go out and read the TSC. Then you could estimate the time to when you really want this departure event to happen. And then you could load the packet with that event time, that estimated departure time. And then you could use TPAUSE or timing mechanism to wait until that event happens. Then you're idle for a little while. The TPAUSE completes, and then you can send the packet with the event time that it was supposed to depart. And so things to consider, if you do have out of order instructions enabled, you want to have some sort of fencing mechanism, because you don't want to wait for the TPAUS to happen, but then the packet is sent, so you need some sort of fencing, such as an mfence instruction. You want to make sure that you do run to completion, that basically nothing can preempt you in having this instruction happen. And you don't want an interrupt to interrupt the process, and then you come back to it, the TPAUS, happened a long time ago, so it moves forward, and thus your packet is sent at a different time than you expected. And you also have to be aware of, what is that idle time going to have, what effect that idle time is going to have on your processor, right? If it affects, like, let's say you had the packet in cache, and then all of a sudden the processor, stops working, that cache gets moved to main memory. Now all of a sudden you have to go out to main memory to get the packet to send it. So you probably need to look into some sort of cache locking mechanism or some cache QoS mechanism so you don't lose the packet. And the event time, may not exactly equal the departure time, but it should be a lot more accurate than normal software timestamps. So let's go back to our love story. So, computers have had significant impact on our hero's lives and the lives of everyone. He would like to give back something to the computer industry to show his appreciation, something that makes computer and computer applications performance better. And he believes that precise time can be that mechanism to help performance, especially in the data center and for data center applications, to work better. And as precise time becomes more available at the processor through PTM, new features can be implemented and new ways of using instructions can be performed. So let's look at precise time as if we're futurists. Okay, so there's this really nice strategy paper from the Harvard Business Review by Amy Webb about how to do strategic planning like a futurist. And it gives a framework, which we show on the right here, that things that are going to happen in the next 1 to 2 years talks about tactics, 2 to 5 years talks about strategy, 5 to 10 years talks about vision, and 10 plus years talks about system evolution. So let's take a futurist view of precise time and applications. So one of the first applications after industrial Ethernet and the power grid that took advantage of precise time is your 5G telecom, your cellular industry. And I think there are going to be improvements on 5G over the next 5 years on top of what we currently have. After that, 5G will move to 6G, and you'll get a lot more network edge related items. And then after 6G, you'll have 7G. And I believe those network edge applications will have tighter and tighter requirements, even at the processor, as we move to next generations. So at OCP TAP, we had a nice presentations about Cockroach DB, about databases needing synchronization. Well, now that you'll have precise time at the processor, I think there are even more advantages that database can take advantage of. And so you'll have more advanced database features that can use precise time. For a while now, 1588 has been used in high frequency trading. You've had MIFID 2. In the future, OCP TAP, we had CloudX as a presentation. And I think there's going to be more precise financial and more precise trading applications that will use precise time. Telemetry, we're seeing a lot of great things happening with telemetry. And I believe that telemetry, which is now in the NICs and in the switches, will now go even further back into the CPUs. Artificial intelligence, I think they're just starting now to look at how we can take advantage of precise time to do artificial intelligence and machine learning using that precise time. Those will become more advanced as we get, use PTM to the XPU, maybe the GPU and other processors that use that do that AI, ML processing as they get the PTM features. And finally, warehouse computing, where you take your data center and you chop it up into computing blocks that can be used by to handle an application. And so, as you can see here, somewhere in this 2 to 5 year range, you see this next generation of things popping up. And that's where I believe PTM at the processor, having that precise time at the processor, is really going to lead to improved application performance and applications that can take care of that, or can handle and use that precise time at the processor. And while I presented a few in the previous slide, there are many different applications that I believe, tens or possibly hundreds of applications that could really take and see significant improvement by using precise time. So our hero's mission is to make computing performance better. How can you help our hero? Well, one thing is you can present your use cases and your data at OCP TAP so others can learn from it. Now, I understand that some of that data and use cases are very proprietary. And so, talk directly to Intel, talk directly to the other vendors that are represented here at OCP TAP so that those vendors can analyze the data and, if appropriate, implement things to make your applications run significantly faster. And neither Intel nor OCP TAP or any other vendors can't fix what they can't see and they can't understand. So by sharing your use cases and your data, you're helping Intel and you're helping the vendors and you're helping the whole OCP TAP community, see the problems that you're seeing now and understand those problems. So one thing you can also do is ask questions, for yourself of your products. Can inefficiencies from being proactive, be reduced with more reactive techniques? For example, driving to the ferry, instead of having that 10 minutes of buffer, by using other tactics, can you reduce your time to 5 nanoseconds, that buffer time? And thus, you're being a little bit more reactive and, thus doing things more efficiently. Can the bottlenecks be analyzed and reduced or even removed, by precise time synchronization? And finally, what proofs of concepts can easily be done? I have this idea that precise time will help me with this application. Well, are there proofs of concepts that can be done easily to prove that, yes, that is the case? And, thinking about this mission to make computing performance better, let's look at some ideas regarding precise time. So let's say you have a brownfield data center, and let's say you have 10 nanoseconds of jitter at all of your interfaces. Well, is there something that we can do the brownfield data center that, we don't want to replace our spine switches, we don't want to replace our Tor switches, we really don't want to replace, all of our racks full of servers. Could we, as OCP TAP, come up with an optical module that implements White Rabbit technologies and place them in the brownfield equipment? For example, for the uplinks. This example shows from any server on one rack to any server on another rack that it's about 90 nanoseconds of jitter when you go through the spine switch. If we were to change the uplinks so that instead of, 10 nanoseconds on those uplinks, you had 2 nanoseconds, now all of a sudden that jitter is reduced by about 40%. And I say 40+% here because that 2 nanoseconds of precision, could affect that 10 nanoseconds indirectly. And even though I showed 2 nanoseconds with White Rabbit, some of the presentations, this could be 200 picoseconds or 20 picoseconds or something like that, making this even more accurate. The next thing is, now that we've considered precision in the data center and trying to make things more precise, consider latency. One of the best papers I've seen on this is this attack of the killer microseconds. In this paper, they talk about how, people are really good at solving the nanosecond problems, and they're also good at solving the millisecond problems. But the microseconds hurt the applications, and you end up with lots of microsecond problems that aren't being resolved. And can we attack those microsecond problems and not have a death by 1,000 cuts or 1,000 microseconds, hurt our application performance? The next thing is think about what you're building. This 10, 15 years ago, the cut-through switch was pretty amazing. The packet could come into the switch and get routed out of the switch before the whole packet made it into the switch. And that was pretty amazing. But then we started creating FECs that were very high in terms of latency and basically, killed the cut-through switch. And then consider your network speed. Here at Intel, we're looking at, 100 gig, 200 gig, 400 gig Ethernet, in the future, 800 gig and 1.6 terabit Ethernet. The faster those Ethernet links are, the lower the latency between the switch and the NICs, or the TORs and the spine switches. And those can help application performance. We talked about how you can use, precise time for scheduling. We talked about precise time for semaphores, but there's also video pacing that could be done. There's a lot of data that needs to be transferred from, for applications like YouTube and Netflix. They need to go from, the data center all the way through the network to your PCs. And here at Intel, we have this Intel Media Transport Library that implements SMPTE ST2110 using the Kawaii API. And, Raul Diaz is the senior PE, or principal engineer at Intel, that's leading this effort. And if you need more information on that, you're welcome to talk to him, or I can put you in contact with him. So for resources, the Software Developers Manual, they'll talk about the TPAWS, the MFENCE, and the RDTSC commands. The no-op wait instruction that I created for the NEOS 2 processor with the help of Dennis, that's available. For NICs, if you're looking for precise time in the NIC, you can look at the 700 series or the 800 series from Intel. And then there's a really nice video that's Intel developed for 5G RAN that I've put here. And I really feel that even though this video highlights what applications can, how applications can improve using precise time for the radio access networking environment, I believe it applies very much for the data center environment. And so in conclusion, I hope you've enjoyed the story about our hero. You learned a few things about precise time technology today and the processor's use of precise time, trends in precise times, and ideas for the future. And hopefully you can help our hero by sharing your use cases and ideas at OCP TAP, so we can learn from them and make compute and application performance better. And I leave you with a question: what wonderful thing can you do with precise time? Thank you. Any questions or comments?
Thank you, Dan. Yeah, let's open the floor for questions. Either unmute and you can ask a question, or put it on the chat. Also, I want to quickly announce that we finally got the PTP support on the CM4. So I'm sharing here. I shared a link with you guys. We're in the process of adding the patches to the mainstream kernel. But if you're eager to get it now, we have the patched kernel in that GitHub repo. So let's get back to the questions. So any questions from the audience? Okay, Dan, I have a question. So
Okay.
when we get to this precise time, let's say the use cases on the processor, what's that of precision is required, let's say?
Well, so it really depends on if you do it at the like an FPGA, or you do it like in a Xeon processor, right? You're asking about what precision is available at the processor, or what precision
What precision is necessary?
is necessary. I think as time moves on, we have to get it into the single-digit nanosecond range, between the processors, uh, on the different racks. I think that ultimately that's where everything is heading. You look at the telecom area, where they have about 5 nanoseconds for class D. I think that eventually, there are a lot of, people that are trying to meet that, or have meet that right now in the telecom industry. My guess is that this will be, soon in the data center, and that they'll take it, one step further, and try and get it, into the single digits.
Georgi, you want to ask
Yeah,
a
I
question?
have a question, and
Mhm.
it's more philosophical, but I think the presentation was great, and it also touched some of this. What is the diminishing return? What is the point of diminishing return? We can continue targeting and get or consider White Rabbit as the shiny object that talks about picosecond. But when we talk about data centers, for
Mhm.
1 nanosecond, the speed of light takes about 30 centimeters. So talking
Mhm.
about single-digit nanosecond, we have to have very specific case. Where do you think is the point of diminishing return of going to better synchronization?
So I think about 1 nanosecond, to me, seems about right. Ideally, sub nanosecond, is there, but yeah, as you mentioned, maybe you're spending too much money to get to that sub nanosecond to get there. But I think, in the near future, 5-10 years from now, a lot of the Macs will have that option, whether it's an in-house design, or, some vendor. But I think that if you understand how you can, it's kind of like the timing engine of a car, right? Or a timing belt of a car. If you have multiple things, like, let's say, warehouse computing, that you're accessing, and you want to access resources in a well-defined manner so that you're pacing things, I think that you need that nanosecond accuracy, so that you can, one, measure the times, the distances to certain resources, the time it's going to take to those resources, and try to, like that timing belt on your car, precisely pace things such that you don't have that congestion, you don't have that um, burstiness that you tend to have in non-synchronized networks. Does that answer your question?
I don't think we have a precise answer for this question. It will be a question coming all the time, and
No.
knowing more, we'll have a slightly different answer. I'm just curious what you think.
Well, so look at the trends, right? In 2006, when, I was working on the IE3000, I think one of our requirements was 500 microseconds, right? Or not 500, it was like a microsecond, or 500 nanoseconds, or something like that. Move forward, when the ITU came out, they're talking about, class D is 5 nanoseconds. Move forward even more, I think we're going to be looking at 1 nanosecond. So I think it's a progression of time. As people find unique ways to squeeze out those extra nanoseconds, you're gonna get it closer and closer to sub nanosecond. And it also really depends on the application, right? 1588, back then they were looking for microsecond resolution for robotics and for energy. As we move forward, the telecom are using it more precisely for, windowing. And as we get into the data center, I think resources can be applied, whether it's through, some sort of gang scheduling method or something like that. But that precision needs to be there. That's in the single digits, or, hopefully, nanosecond or sub-nanosecond precision.
I find the telecom to be a very special case because they need to affect the physical reality. So they need to have windowing, they need to have some frequencies, and that define the data center is a different case. We have no CPU that's capable to execute hundreds of instructions for 1 nanosecond. In fact, the tendency seems to be having more cores and lower frequency. So today in 5 gigahertz CPU, you can execute probably 5 instructions for 1 nanosecond. So getting to the point where I have, let's say, 10 nanoseconds error, I don't know what to do with this error because I cannot execute anything meaningful for this small period of time. When we talk about communication between two machines, when we talk about the same CPU, obviously we can do a few things. So I don't have a good answer either, and I think we need to find a good way to explain why going to 1 nanoseconds makes sense in the data center.
Wouldn't the 5 gigahertz and running instructions at, let's say, 200 picosecond push, let's say, the requirement for like scheduling, like, let's say, instructions between processors down to that region as well? Or, I mean, if we want to be respectful to Nyquist, maybe, like, I don't know, you have to have even lower, like.
Yeah, if that's the case, what, you want to have it 100 picoseconds precision, but I think, less than.
But this is for one instruction, and I don't know what I can do. It's even not the whole instruction on x86. It's probably something more. I mean, something.
The important part is that you somewhere will probably serialize all those the results of the instructions, right? Whether it's on the NIC or in the some accelerator, and if you have better resolution there, you can schedule more granularly.
Correct. And I think you also have to understand the access of resources, right? If you have, you say the number of processors is increasing, right? And, it was, 4, then 8, then 16, 32, 64, and, soon there might be, thousands of processors all running at 5 gigahertz. And if that's the case, then it's almost like that timing belt situation where you may want, in other words, you may want all the processors to have a certain slot where they can access resources. These could be shared ALUs, that a subset of them can access, or it could be, external memory resources or something like that. And I think that's kind of where, when you're at the instruction level, kind of like what I was showing, earlier, disadvantage of animating, right? In this case, where if you stagger it in terms of 10 nanoseconds or some window, you only have usually one PCIe interface, going in and out, or one, resource like that every processor needs to take advantage of. If everybody's trying to access that say PCIe or CXL resource, all of a sudden, if they're accessing at the same time, because of the wire, they cannot all transmit across that at the same time. So if you stagger the processing or stagger the applications, you could basically, get rid of the burstiness and try and make things relatively smooth for that, scarce resource.
Yeah, the timing belt, it's a very good comparison. I really like it.
Yeah. So, like, looking at two processors on the same board, or like the UPI connection between processors, aware of like, I don't know, what's the precision in terms of sync between the two CPUs?
Yeah, I don't have that information. I don't know if Kevin Stanton's online, but I don't have that information of two processors.
Or I think
I think Chris Hall
Chris,
presented, yeah,
Chris, do you have
he,
any insight on that?
I don't know if he has it, but I mean, he was showing with PTM that, you know, he was getting what, about 10 nanoseconds of precision across PTM. And so, you know, it might be possible if we use, I don't know what they use across that interface. So, but
Yeah.
my guess is it would probably be in a similar range, or they may be more precise, but I don't have that information to give you right now.
Yeah. I mean, I think it's not a bad let's say in the wish list or like a whatever, like a target to
Right,
aim for, where you have multi-processors, but now it's across the network. I mean, there's
right,
a lot of things you can do to, let's say, build such thing. Like considering, let's say, you can have the NIC basically becoming also the root complex, and then now you have all the NICs in the network that like all the NIC is like the backbone with precision time, and now
right,
every computer is basically just adding like enumerating like new devices on one coherent like network backbone. So I don't know, such thing. Anyone here like I don't know is familiar with something like this? That I don't know. I've been thinking about it like how what can be done like let's say for the next generation of like using like evolving networks with the presence of precision time.
yeah. I think there's a lot of innovation that can happen in this area, and
Yeah.
yeah, I think the NIC is, you know, in a very important place to, you know, understand the needs of all the processors at the other side. You know, for example,
Yeah.
if you're in a co-location kind of situation where you have a cloud service provider and a uh, an ISP, internet service provider, uh, or a telco at the same location, you know, that NIC has the ability to control the time, you know, that the application sees in the future. I don't think it has the ability to do that right now. It may, but I'm not aware of
Yeah.
it. But I see that as something that's going to be important in the future. Is, you know, let's say I'm buying something from Amazon through my Verizon cell phone. You know, if I want a response quickly, you know, maybe I'll, you know, talk to the Verizon data center, and that data center will have, you know, the cloud service provider, you know, servers right there that can give me a response very, very quickly. And so, and I think the NIC and
Another
the
thing, like
time.
speaking of Nick, is I mean, I think we've been discussing this for a while now.
Hmm.
We're thinking like right now, let's say, yeah, you have all this precision time and everything and so on. Let's say when it comes to a higher level of, let's say, these logics, the, the, the management schemes,
Hmm.
you have them all executed at layer 7. So let's say things that like distribution, broadcasting, atomic operation. I don't know, you name it, it
Right,
just keeps going on. The list goes on and on. These
right,
are done in layer 7. While if the NIC takes over these things, let's say, for example, you give the NIC, hey, this, and share it with these peers. And
right.
then, like, I don't know, share it with, like, in a timely manner that, like, if they have something earlier, don't bother, right?
Yep,
And then if you have something like this, um, like if you execute something like this on the NIC, it will make the like today's NICs look like how back in the time, and I think it was at 8088 or 8086, I don't know, like when there was no graphic card and the CPU had to raster the monitor, and
right,
now you have the graphic card taking care of that, and you just put one time in the like the video RAM, and then everything is taken care of. The sequencer takes care of everything. So
Right.
perhaps something similar should come for the NICs. And I mean, you always have the option to go like lower level, and then you send it exactly from this to that, but you let the NIC take care of most of these things. And I think that's the concept, I think, for the smart NIC. And
Exactly. Yeah, I mean, you know, going back 20 years, we were looking at TCP offload engines, right? And now the accelerators are getting more and more, you know, higher level, as you say.
Yeah.
And so there's no reason that in the future, you know, there can't be accelerators on NICs to do things like security and other higher level functions.
yes.
And so,
Okay, great. Any more questions before we give you back the rest of the time? Calling once, calling twice. I think that's it. Okay, Dan, thank you very much again for today's presentation, and to everyone, enjoy the rest of your day.
thank you, everyone.
Thank you. Bye.
Bye.
Bye.